The four fundamental forces, what we were discussing in the last video, are all part of what's known as the standard model of particle physics, which is a language unto itself, but a very robust and well-established one, even if it seems mysterious to us. But there is an aspect of the standard model that's been understood for years to be an integral part of what describes the nature of reality. That isn't something that most of us think about very much, but it's really an important one, and it's just recently been mostly answered, or has had the potential to be answered, in the Big Particle Accelerator in CERN, the Large Hadron Collider. And it's essentially one of the most fundamental questions of nature, which is, why does matter have mass? What causes particles to have mass? And it seems like that is almost a silly question to ask, but it's not when you consider, for instance, that the photon has no mass, yet it has particle-like nature. In any case, the particle in question that they've been investigating and searching for is known as
the Higgs Boson.
Yes, the Higgs Boson, or what's also known as the Higgs field. And particles interact with this field in such a way to have their mass be manifested based on the nature of that interaction. Again, beyond the reach of our discussion here very deeply, but it certainly relates to the force particle masses as well, which dictates the nature of the forces in the particle exchange theory that we've been talking about, which we're trying to unify. All these forces, attempting to unify, all this comes together in a very nice, neat package in the mind of the theoretical physicists doing these investigations. In any case, an overview of the unification, kind of starting from the right, where we have the magnetic, electric, weak and strong, and gravity. Those aren't really five forces. Magnetism and electricity have been unified for a long time in the sense that really it's one force called electromagnetism. And that electromagnetic and the weak force merge into what's called the Electroweak Force. Along with the strong nuclear force, kind of going to the left here, is going back in time toward higher energies in the universe and higher temperatures to produce what's known as the grand unification, or GUT theories, gut theories, where the forces are unified. But the really sticky one is gravity, universal gravitation, and how that unifies with the other three forces into super unification, or what's often called TOE theories, a theory of everything, where everything, all in particular, all the forces are combined into one. And string theory, quantum gravity are topics that are associated with the synthesis of all those forces of nature to give us an understanding of the essence of what the stuff in the universe is made out of. So just to show you one more diagram about this unification idea, we have a chart here showing up at the top is time. This is now, currently. As we go to the right, we're going back toward the beginning, the origin of things. Along with that, in early epochs, we had temperature rising through the roof, so to speak, and interaction strength of the forces and particles that we've been discussing. So at very early epochs, everything was unified into one superforce, incomprehensibly high temperatures. And as time goes on, as we see time progressing here, we see the splitting off of these various forces. So gravity splits off first at very early times and very high temperatures, okay? And then we enter the grand unified theories, where the other three forces are one. They split off from the strong nuclear and then the electroweak, till we get to the limit of the investigation of particle accelerators, where we have actually been able to confirm the merging of the electromagnetic and the weak force into the electroweak. So that's been experimentally confirmed. But as we go toward the left, we're going toward our current era. Actually, when the electromagnetic and weak forces split off from each other, then from that point on, up to the current time, we have the four forces being distinct, no longer being combined into one. So that's all we see now in our everyday lives. But this electromagnetic and weak were actually experimentally verified in particle accelerators. So that puts a little bit of realism to this. This isn't all just theoretical. So that's just an overview of the unification idea of the fundamental forces. This graphic here shows a brief, highly logarithmic, compressed time scale here of the history of our universe from the very early epochs of force unification and the emergence of them into distinct forces, particles, atoms emerging, the galaxies, right up to the current time, where we've got basically 13.8 billion years here. And the first very small fraction of a second is what we've just been talking about. Some key events that took place. This is a whole course in and of itself. That would be a study of the history of the cosmos. But that's just a picture to perhaps pique your interest that there's a lot of richness in our understanding of the development of particles and all the way up to people. And people are pretty important. I'm sure you'd agree with me.